Hi everyone, welcome to Espressif's Developer Conference 2024. I'm Amit Chet. I'm an engineering manager at Espressif. I have 12 plus years of experience in embedded domain, and currently I'm part of a team which looks after secure manufacturing solutions at Espressif. Thank you.
Hello everyone, I am Aditya Bhatwardhan. I am senior software engineer at Espressif. I have been working at Espressif since last 5 years and I have actively contributed in the bring up of security peripherals for ESP32 system of chips. My areas of expertise are embedded systems, networking and RTOS. And I have been actively contributing to the crafting of secure solutions at Espressif.
Hi everyone, my name is Dhaval Gujar. I'm a senior engineer at Espressif, and I currently work on the AWS IoT Express Link project, the Zero Code EXL project, and I'm part of the team that works on the secure manufacturing project at Espressif.
Yeah, so today's talk is about secure manufacturing services. To provide a brief preface to this entire talk, is that in the ever evolving landscape of IoT, the application complexity has gone quite up these days, and naturally, the manufacturing complexity along with it has gone up as well. Um, in this evolution, the mainly focus has been the security of the overall offering, and that really puts a focus on security of the overall manufacturing process as well. So that's what we will probably talk about in this talk, which is how manufacturing services can be secured. So there are few compliances and regulations that have been put in place by various countries for launching various IoT devices, such as US Cybersecurity Trust Mark, CRA from EU, CLS Singapore, Matter, as we probably all know, is a new smart home protocol, which also has some compliance requirements. So yeah, overall. This really puts a focus on the security of manufacturing the modules or chipsets, and manufacturing process also is a part of overall product security. So our today's agenda is mainly to discuss various aspects of how a secure IoT manufacturing process should look like, and what has Espressif in the offering for such a secure manufacturing solution. So that's what we'll be going over in this one. So moving on, the why should developers really know about manufacturing process? These days, security cannot be an afterthought anymore. Security has to be considered at the onset of the project itself. Even the supply chain security has to be considered when a developer is developing an application. And along with that, developers it is should know that how to generate and protect an individualized credentials for a fleet of devices. While developers are creating the application, it is quite common that they deal with a single device, but it pays to know about how to scale this individualized credentials for millions of devices. That's where knowing about how secure manufacturing services operate comes into the picture. Similarly, developers can also leverage capabilities of secure manufacturing services, such as creating and flashing manufacturing time data securely, and burning custom MAC addresses as well. So, if their application requires some sort of custom data that which can be unique to every device, or they can also be same for all the devices, they can probably, if they know about secure manufacturing services and how they handle such data, it helps them visualize and design their applications around it from the start of their project itself. So our next is what are the complexities and considerations of typical secure manufacturing service? Typically, a manufacturing service should consider how per device unique data are generated and flashed and protected on the device, and similarly how the security is ensured uh, at the manufacturing stations or the manufacturing factories. So for per unique device, there is identity of a device that needs to be generated while at the manufacturing station, and it also needs to be protected at the same time, so that the device, the data or the sensitive data of the device is not getting leaked when it is changing hands from manufacturing stations to any contract manufacturer and then to the eventual ODM or the customer. So preventing this leakage of sensitive information is of paramount importance when considering or about the secure manufacturing services. Similarly, how to generate custom data for every module is also one of the considerations for secure manufacturing service. And there are three major buckets of security that one needs to think about when designing such a service, which is a platform security, which includes enabling secure boot, flash encryption on the device, which is a part of many of our Espressif chipsets. And similarly, supply chain security, as we spoke, supply chain security is where no sensitive data is getting leaked when modules change hands from manufacturing line to any intermediary and to the eventual customers. Similarly, we also need to ensure that manufacturing time process security is also maintained, wherein even the manufacturing stations cannot read out any sensitive information because the factories are usually third party factories. So that is another part that one needs to consider while designing any secure manufacturing services. I will let my colleague Aditya tell you about all these requirements in detail. So over to you, Aditya. Thank you.
Hello all. So let us take a look at the per device unique data. So in that there are mainly two parts. First is the device identity. In this Internet of Things, there are millions and billions of devices. So uniquely identifying each device and also ensuring that the identity itself is unique is important. Additionally, some custom data which is important for a particular product, which also needs to be secured. That and its security is also important. So let us take a look at how the identity is generated on the device. So each device has a random number generator. So random number generator is a hardware which shall generate truly random numbers once sufficient entropy sources are enabled. So all of the Espressif SoCs have such a random number generator. With that help of that random number generator, we can generate the device private key. The device private key is a random number, and based on the algorithm used for a private key, such as RSA, ECDSA, it can be ensured that it is present on that particular curve. So um, with help of random number generator, we will generate the device private key, and each device private key has its associated device public key. So together, they form one cryptographic key pair. Similar such key pair is available for a cloud authority. So in this case, the device private key and device public key um, will be used to generate a certificate signing request. It will contain some information which is relevant to that particular device, such as the common name of that device, which is unique, additional information about the product. Such things will go into the certificate signing request, and it will form the complete certificate signing request, which will then be signed by the cloud authority. So now this cloud authority, when it signs the CSR, the end result is that we get the device certificate. This device certificate is a public entity and can be shared with anyone. As this device certificate has been generated with a CSR which was associated with the device private key, these two, device private key and the device public key, that device certificate, form the unique device identity in its entirety. So this will be the thing that will uniquely identify that particular device in the Internet of Things. So, as we've seen, the unique private key forms the unique identity for the device. Ensuring its protection is crucial because if someone gets access to the device private key, then an attacker can also pose as the original device. So, ensuring the protection of this unique private key is really important. For this, in the secure manufacturing workflow, one important step that needs to be considered is generating the unique private key on the device itself. When you generate the private key on the device, it should never leave the device, and when it has been generated, it should be protected immediately. How it can be protected? It can with on the Espressif system of chips, there are multiple hardware peripherals available, such as the RSA digital signature peripheral, the ECDSA peripheral, also HMAC peripheral. So, all of these hardware peripherals which store the key itself or some secret to encrypt the key in the hardware, that is the effuse of the SoC. So that way, when you involve the hardware, the security of the key greatly enhances. Additional to that, the custom data also needs to be protected. This data can be the one-time manufacturing data, which is unique for some fleet of devices, or some custom MAC addresses, which are typical for that particular product. Additional to that, there might be some sensitive data, such as salts and verifiers, which are used as cryptographic authenticators in several algorithms. That data can form this custom data, which is also important to protect this. So now let us take a look at the security aspect of the secure manufacturing. So the first part in platform security is flash encryption. Flash encryption on ESP32 is a security feature designed to protect the contents of the device's off-chip flash memory. When enabled, the firmware is stored in encrypted format on the flash of the device. This ensures that even if someone physically accesses the flash memory, they cannot get the plain text contents of the flash. This is crucial for protecting sensitive information such as encryption keys, user data, or proprietary code. It is important to enable the flash encryption as a part of the secure manufacturing process so as to protect the software IP of the customer or some device secrets that may rely on the device's ability to encrypt its flash. Now we come to the second part, that is secure boot. Secure boot is a security feature designed to protect devices from executing unauthorized or unsigned code during the boot process. While flash encryption allows us to encrypt the data on the flash and any attacker cannot read the data directly. If the attacker has the ability to execute unauthorized code, then they may bypass this free feature and get the plain text contents of the data. Hence, it is really important to also enable secure boot as a part of the manufacturing itself to make it secure. The third and important part is the device hardening. While enabling both of these features, it is important to also disable all the available debug interfaces such as JTAG, etc., so that these interfaces do not pose a threat to the security of the device. To ensure that all these debug interfaces are disabled correctly, Espressif has provided two APIs in the EISP IDF environment. In this case, you could use the two APIs mentioned in the presentation, that is the verify release mode for flash encryption and verify release mode for the secure boot. These APIs would ensure that all of the debug interfaces are disabled and the device is in the correct state and can be considered as secure. Uh, Now let us take a look at supply chain security. So typically, the factories which are responsible for manufacturing the modules are third-party entities. Although many of these factories offer secure infrastructure, it is crucial to design the manufacturing process itself in such a way that the data exposure to any external entities is minimum. The sensitive data such as device secrets or cryptographic key should not be accessible to any outside entity. Additional to that, the entire process should be atomic. The atomic process of manufacturing ensures that no outside entity has access to the sensitive information or some arbitrary information generated while executing the manufacturing process. Similarly, in the manufacturing process security, we have to ensure that after the device has been manufactured, the device does not pose any interfaces with which the outside entities or the host station are able to access or extract any of the critical information, such as the private keys or some per device unique data. We should leave the device in such a state after the atomic process of manufacturing so that no external entity can uh, obtain any data from the device. While securing the device itself is one aspect, securing the certificate authority is also an important part. In manufacturing, as we've already seen, the certificate authority is used to sign the device certificate. It is important to store these certificate authority or typically the private key of that certificate authority in a FIPS 142 level 3 standard given by NIST. This ensures the protection of the CA private key and ensures that that particular key is not leaked to the outside world. Otherwise, fake device certificates can be generated with that key.
Thanks, Aditya. Now let's talk about Espressif's secure pre-provisioning service, which is an implementation of the secure manufacturing uh, that we just talked about. So my colleagues mentioned to you the complexities and considerations that one needs to take into account when they are thinking about a secure manufacturing service. Espressif provides the secure pre-provisioning service as a way for implementing these. Let's go through the entire flow once. So it starts with taking information from the device maker about their SoC, the private key algorithm. It may be RSA, ECDSA, the number of bits for that particular private key, and any other customization requests like custom data, custom MAC addresses, so on and so forth. Now, for this workflow, I'm showing an ESP32C series module, but this can be any of the modules that Espressif manufactures. So in the first stage, we have the manufacturing test station, which is an entity that is connecting to the ESP module. The module is typically placed in some sort of a jig, and the connectivity is established over UART. The device under test, that is the ESP module, is running a custom firmware, which accepts commands as well as data over the same UART from the manufacturing test station. Now, the command that the host or the test station sends to the DUT is based on the configuration. For example, if you want an RSA private key to be generated by the ESP device of 204 bits in size, the command would internally be something like generate RSA key 2048 bits. Now, there are other pieces of information apart from the algorithm that also go from the manufacturing test station to the device. For example, the common name of the certificate that needs to be generated. In addition to that, the security features that would want to be that you would want to enable are also provided to the ESP device. At this stage, the device has obtained all of the information that it needs in order to carry out the operations independently regarding the generation of the private credentials. We talked earlier about how the uniqueness of this information is extremely important, and using the hardware RNG peripheral for doing so. So in this stage, the hardware RNG peripheral is utilized for creating the private key based on the algorithm that was chosen earlier. In addition to that, this method of generating the private key on the device ensures the uniqueness of this. Now, the device has created a certificate signing request. What is the information that the CSR contains? The CSR contains the common name, which it originally received from the manufacturing test station. In addition to that, the CSR contains the public key, which was generated from the private key by the device itself. Note here that the only information that is going in the CSR is completely public. The private key has not left the device at this stage. And now this CSR, which is, as I mentioned, public, goes over the UART back to the manufacturing station. Now, the manufacturing station does not actually do anything with the CSR itself. All it is doing is acting as an intermediary that sends this CSR to a certificate authority. Here, the assumption is that there is a secure session that is established between the manufacturing test station and the certificate authority when it is sending the CSR. The secure session is not because the CSR itself contains anything sensitive. It is to ensure that only authenticated entities can actually get CSRs signed from the certificate authority. Now, the certificate authority is what I'm referring to as the storage of the private key and some kind of an API to sign that particular CSR. The CA private key is extremely important to the whole setup, because if that is compromised, then anyone can create counterfeit devices, as Aditya explained. So people typically opt for a cloud-based or a physical HSM, and Espressif has support for both. In addition to that, there are non-reputable logs that get generated at the level of the certificate authority, which can show you exactly the number of signing requests that were carried out. You can compare and contrast this with the actual modules that you receive from Espressif to ensure that no additional signings were carried out and no other devices in the world exist apart from the ones that you have received from Espressif. Now, after signing the CSR, what gets generated is the device leaf certificate or the end device certificate that it requires to communicate with entities like the cloud or for anything else. So the CA sends this leaf certificate to the manufacturing test station, and the test station again does nothing else with the certificate apart from parsing it just to verify the integrity of the certificate, and then sends it to the DUT. In addition to sending the device leaf certificate, the CA might also provide the actual certificate that it used to sign the CSR. This is just for some kind of applications where you would want the CA to also be residing on the device itself. So this was mentioned earlier. I just want to reiterate, the device leaf certificate is itself not sensitive. It's public and can be sent over plain text UART to the device. Now, there is a certificate program request issued from the host, which is the manufacturing test station, to the device under test. At this stage, the device has all the information that it needs to securely store in its flash memory. And in addition to the flash memory, any of the other secure components that are offered, for example, the HMAC peripheral, the ECDSA peripheral, or the RSA peripheral. So at this stage, the DUT burns any of the appropriate eFuses that it requires in order to keep the information secure. If the customer has opted to enable secure boot or flash encryption, all of those are enabled at this stage itself. So when you receive a pre-provisioned module from Espressif, it already has the entire security configuration that you require, in addition to having the security credentials. Finally, the DUT sends back an acknowledgement to the manufacturing test station, which gets logged by the test station so that any module can be traced back to this process, and you can see exactly what steps were carried out. As a part of this acknowledgement, the manufacturing test station is also able to tell whether the appropriate security configuration was applied on the device. When you receive pre-provisioned modules back from Espressif, they are not just modules that you receive. In addition to that, you receive a manifest file. A manifest file is a simple CSV which includes the MAC address of the device, which is a physical identifier for that particular module. It has the common name of the certificate, and it has the certificate itself. Usually, this information is uh, used for registering all of these devices in bulk to any cloud of your choice. And it also can be used to generate necessary QR code information, which is therefore which is what you get on the device packaging itself. So that's an overview of Espressif's pre-provisioning service, which is an implementation of our secure manufacturing best practices. Thank you.